piezoelectrics and using piezoceramic materials to gather power. So we're interested in small systems that we can put on actually living organisms, large insects, small birds. So right now we're looking at a couple of methods of gathering power. In addition to piezoelectrics, we're also looking at very, very small voice coils, or small coils that interact with magnets in order to generate power as well. And the reason why we're sort of doing both is because the power that you get from a magnet is proportional to velocity, and the power you get from a piezo is proportional to displacement. So by having both of those working in unison, now we have an ability to get power out of phase from each other, so we can put more power on the supply or on the capacitor. So unlike many sort of research that we've seen in energy harvesting, we're also interested in how do we take power from sort of disparate sources like solenoids, electromagnetics, or piezoelectrics, vibrating type structures, and harvest all that onto one source. So we're looking at electronics to impedance match or match the gathering of charge onto a capacitor, and then shift it onto a permanent like supercapacitor that would last like a 24-hour power source. So we're thinking about energy harvesting sort of in a systematic way, almost like you would think about a hybrid car. It's not just, can we gather power here and put it across the resistor and say, aha, there's power consumed, but can we do something that's a little more systemic for two reasons. One, we want to be able to, in some ways, think about not just harvesting, but scavenging. Can we get power from different sources, wherever they may be, and put it all together to get all that energy onto one supply? And in doing so, how do we get the different pathways to all work in unison? So it becomes a complicated circuit with lots of switching technology, lots of impedance matching or resistance matching sorts of issues, so that the power flows most efficiently from each different source. One of the things we're looking at actually is fundamental mechanics. Like if you just take a structure, a straight structure, and you look at it, I'd say a good half to maybe approaching almost 2/3 is dead structure. It's not actually involved in harvesting energy. So if you look at a simple structure that is cantilevered or just vibrates from its end, most of that structure is not gathering power for you. In fact, you have to shape the structure to match the shape of the strain actually within the structure to make the most efficient actuator you can. And we're looking at problems like that because we're driven by our challenge that is small enough to be put on a 3 or 4 ounce sparrow, or small enough to be put on a 20-gram insect. So we're challenged by the task in front of us, and it makes us in some sense do the engineering more carefully. So we're sort of coming up with ways of building circuits to most efficiently use every little bit of power we can generate, and also use the shape as efficiently as possible. Even the idea of combining the magnet with the piezo came from the fact that the literature, if you look at the solution to the problem, it wants you to have a little tip mass on the end of your little piezo beam, but rather than have something that's dead, that's not giving us any benefit, our tip mass is going to help us gather power. So we're sort of driven by trying to squeeze as much energy per unit weight as possible. You're completely lost without our entomology colleagues, physiologists, entomologists. They are our native guides to this strange land for engineers. Well, we'll just attach this to the nerve, and they're like, excuse me, the nerve is 1 micron wide. Do you know what 1 micron is? It's about a 25th or a 50th of a human hair. Do you really think you're going to get a probe in that with your naked eye? I don't think so. So again, you have to have these groundings in reality from what exists in nature, and really sort of the nanostructure of nature, or the crudity of our human-made machines. So we're trying to intersect this world of sort of elegance and nano architecture from the atomic scale with these sort of crude, primitive devices. And it is just a challenge and it's you're sort of in awe sometimes with what nature does with so little. There's a lot to learn about how machines can interact with living organisms. I mean, when you think about what we do here in the beginning of the 21st century, if you lose a leg or an arm, maybe it's high-tech, maybe it's composite, maybe it's spring-like, maybe it's all these wonderful passive design things, but it's not robotic, and it doesn't interact with the human body. It doesn't interact with your nerves. It can't give information back to your nervous system. In some ways, it's rather primitive, an improvement on what we used to do maybe in the 19th century, but still just an improvement only in material properties or an improvement in strength to weight ratio. But the methods of attachment, the methods of integration are still rather primitive. We get somebody who's a paraplegic and we give them a chair with wheels, which is what we've been doing for hundreds of years. So the question is can machines interact better with biology? Scaling up is an issue, sure. Nobody's paying us right now to scale up, but it's funny, some of the same things would exist. How do I most efficiently use all the power that I generate? Well, if you have just a passive circuit, a circuit that doesn't change, that doesn't switch or adapt its impedance or the way it interacts with your generation, then you're going to be wasting power again. So I think whenever you go through the trouble of building a power harvesting device, it means you're power hungry. You don't want to plug in and you don't want a battery. And the more power you can get, the better. So I think that at least the issue of using your circuit efficiently is going to still exist at the macro scale. I think that what happens is that other actuators will become attractive at a larger scale. So it may be, at some point you want to spin a windmill, right? So you don't want a small structure that vibrates, but you want something that actually rotates with a revolute joint. So you see large windmills that aren't little vibrating things, they're turbine-like things. And so I think it depends on the scale. I'm thinking about like long endurance robotics. People use batteries in robotic systems a lot, and that bothers me, but I think that might be more of an engineering problem than a truly creative scientific one. Almost like, why don't we just a hybrid car, well, a hybrid robot. I started one thing when I was at DARPA, and I call like chemohydraulics, combining or merging the idea of an internal combustion engine with a hydraulic compressor. So something would be kind of beating, if you will, and pulsing, and yet energizing itself and energizing the hydraulic system. So the combustion process of an engine is perverted to also do hydraulic compression. So it's not two separate things with a crude, shaft spinning between them, but it's sort of one machine that sort of pulsates and is in some sense alive. But chemical bond energy is huge compared to batteries. Orders of magnitude more power. And yet, I think robotics in general suffers from a lack of proliferation because it's just not energetically efficient. Why we don't see more robotics in the military is because we don't have power sources that allow robots to be more than toys. We have to have long endurance machines that could spend the day on the battlefield like our soldiers do, or long endurance machines to do exploration. And right now machines, batteries are 200 to 300 watt hours per kilogram. We know the specifics and we're hitting the limits of chemistry. When we try and get batteries with much more power, occasionally they burn on us. So we're just sort of hitting the limits of chemistry there, and I think we have to think differently about power sources and think differently about, how do we miniaturize those power sources to drive the machines around us. I do weird engineering, that's my thing. The third project we're working on is like an ornithopter, a flapping, flying machine, like a bird, like a biomimetic propulsion system for a very small aircraft. And we think that we can get this thing to fly through the air. In fact, we know we can, and to land. But that's not the weird part. The weird part is we think we can perch it on the edge of a building and then let the wind blow over the wings and then drive the motor in reverse and then power the whole thing up again so it can take off again and fly forever. So it would be sort of animatronic in the sense that it would be like this machine that would perpetually fly in the environment. And we call that the wing mill. So the wing would gather power from the ambient air when it's not flying and then deliver that. You can just give it some sort of programming to go and exist, and it would continually fly in the environment until something tries to eat it, perhaps. I suppose, like anything else. I think the goal would just be to get it to work. I think that would be a goal in and of itself. So I would say that's less funded, but we're having a lot of fun with it. But right now we're working out all the mechanics and the controls so that we can get something to fly in forward flight, get it to hover, and eventually get it to perch. And then the other thing that would be really fun is to actually get it to harvest power by just changing its wings just a little bit So rather than putting energy into the environment to fly, it can suck energy out of the environment to store it.